Hey everyone, my name is Manish, and in this video I'm going to tell you how to automatically generate tests with precise oracles from structured natural language software specifications. Given a software under test that takes some input and produces some output, we need test oracle to verify if the produced output is correct or incorrect. Even today, with the state-of-the-art test generation tools, it is relatively easy to generate test inputs, but it is hard to generate test oracles. And this is called the test oracle problem. Our solution to the test oracle problem is an approach and a tool called Swami that takes as input structured informal specifications, such as the one shown here, which describes how array constructor should be implemented in JavaScript compilers, and this specification is taken from official JavaScript specification document. And Swami generates executable tests that contain test oracles, which are derived from such specifications, and test inputs that can be used to exercise the derived test oracles. Swami is available for free to download and reuse at our website swami.cs.umass.edu. We evaluated Swami using official JavaScript specifications because they do not get deprecated as they are maintained by a standard body called ECMA. They are less ambiguous because they are well written and well formatted, unlike developer written code comments or unstructured bug reports. And last but not the least, there are multiple real world projects that adhere to these specifications, for example, Mozilla Rhino and Node.js. This gives us a very good data set to evaluate Swami's approach on. When we use Swami to generate tests from official JavaScript specification, we found that Swami generated 83,000 tests. Of these tests, around 60% were innocuous. These are the tests that can never fail and therefore can never generate any false alarms. I'll come back to it later why Swami ends up generating these tests, but for now let's focus on the non-innocuous tests. Analyzing the non-innocuous tests, we found that 39% of the total tests were good. These are the tests that captured the specification precisely and would fail on buggy implementation. And only 0.6% of the tests were bad or raised false alarms. These are the tests that incorrectly understand the specification and fail even though the implementation is correct. Thus, we found that of the non-innocuous tests, 98.4% are good and only 1.6% are bad. These results show that Swami-generated tests are precise to the specification. Next, we wanted to see whether Swami-generated tests added any value to the existing developer-written tests. So we used Swami-generated tests to evaluate two large open-source JavaScript engines, Mozilla Rhino and Node.js. And we found 15 missing features in Rhino, one unknown bug in Rhino and Node.js, and 18 semantic disambiguities in JavaScript specifications, which were interpreted differently by Mozilla Rhino and Node.js developers. We also did code coverage analysis in which we augmented developer tests with Swami tests, and we found that augmented test suite covered code which was previously missed by developer tests. These results show that Swami tests complement developer written tests and therefore do add value to them. Next, we compared Swami's performance with respect to the state-of-the-art test generation tools such as EvoSuite. We use EvoSuite to generate tests for Mozilla Rhino. And when we compared the number of false alarms, we found that Swami generated 74% fewer false alarms than EvoSuite. We also did code coverage analysis and we found that when we augmented EvoSuite tests with Swami tests, the augmented test suite covered code which was previously missed by EvoSuite tests. These results show that Swami tests complement EvoSuite generated tests. Finally, we wanted to identify how Swami performs in identifying the specifications that encode testable behavior. It is important to note that input to Swami is not a single specification but a specification document that contains a lot of sections and subsections, not all of which encode testable behavior. Now, depending upon whether the format of the specification document is known or not, Swami uses two different approaches to identify relevant specifications. When the format of the specification document is known, Swami uses rule-based approach for which Swami's precision was 100% and recall was 54% in identifying the relevant specifications. And when the format of the specification document is not known, Swami uses an information retrieval based approach for which Swami's precision was 79% and recall was 99.9%. However, the 21% of the irrelevant specifications got pruned away in the later stages of Swami, giving us an effective precision of 100% using either of the approaches. Thus, Swami identifies relevant specifications precisely. Now let me tell you why it is hard to derive oracles from informal specifications, or in general why the test oracle problem is hard. The slide shows you the table of contents of the official JavaScript specification which we use to evaluate Swami's approach. And as you can see, there are a lot of sections for which it doesn't make sense to generate tests. For example, scope, conformance, normative references, and so on and so forth. So the first challenge to address the test oracle problem is to identify the specifications that encode testable behavior. Now, given a relevant specification which encodes testable behavior, such as this one shown here, which tells you how the array constructor should work in JavaScript, it may contain abstract operations, which are the methods that are created in the specification document to enhance its readability, but are not actually implemented in the software. For example, there does not exist any such method called toUint32 in JavaScript. Thus, the second challenge is to handle such abstract operations. The third challenge is to deal with implicit operations. As these are natural language specifications, most of the times the mathematical or the logical operations are described using natural language phrases. For example, this slide shows you the phrases like is equal to, is not equal to, is not, is positive, is negative, and so on and so forth. The fourth challenge is to actually identify the oracles that are often embedded in the conditional statements and to be able to extract the condition and the oracles. For example, in this case, the oracle describes a range error should be thrown when the length, which is the argument of the array constructor, is a number and 2int32 of length is not equal to length. So if the argument length is not an unsigned 32-bit integer, a range error should be thrown. So we need to be able to identify such conditions and oracles. The fifth challenge is to deal with assignment statements that often use local variables. This is similar to abstract operations. To enhance the readability of the spec, sometimes specifications use these assignment statements. For example, here the slide shows you an assignment statement. Let array be the result of calling toObject on this value. Here the variable array is a local variable and may not be actually implemented in the software. Thus, we need to be able to manage these local variables, which are often used to describe oracles that are embedded in the conditional statements. And last but not the least, since these are natural language specifications, they are ambiguous and can get deprecated. Now, in light of all these challenges, let's take a look at what the state-of-the-art tools can do. The most popular tools, such as EvoSuite and Randu, which derive tests from the implemented source code, cannot derive oracles from natural language specifications. Further, the tests that are generated using these tools cannot identify features that are specified and are missing in the implementation. Also, they cannot identify bugs that could expose the implementation whose behavior is inconsistent with the specification. The more recent tools such as JDoctor, Turadoku, and Tcomment that address some of the limitations of Randu are closely tied to Javadoc because These tools derive test oracles from Java documents and augment random-generated tests. Thus, state-of-the-art tools cannot derive test oracles from informal specifications that exist independent of the source code. Now let's try to understand what kind of oracles exist in informal specifications. The slide shows to you the specification of the plus operator as specified in the JavaScript specification document. It says that the plus operator performs addition when applied to two operands of numeric type, producing the sum of the operands. Thus, for the common inputs such as 2 plus 3, the specification describes a very vague oracle. However, for the uncommon inputs such as positive infinity and negative infinity, the specification says that the sum of the two infinities of opposite sign is not a number. Thus, we found that most of the time the specifications describe very vague oracles for common inputs, and therefore it becomes hard to derive oracles for them. However, for the uncommon inputs, which often lead to an exception or boundary condition, the specifications describe concrete oracles which can be automatically extracted. Thus, informal specifications typically contain oracles for exceptions and boundary conditions which can be automatically extracted. This brings us to a follow-up question which states that is it useful to generate tests only for exceptions and boundary conditions? In 2016, Goffey and others performed a study in which they took 10 popular well-tested open source libraries and they compared the coverage of developer tests on throw statements that correspond to exceptions with the overall coverage. They found that for all the libraries, the coverage of throw statements was significantly lower than the overall coverage, and on average, it was 25% less than overall coverage. This shows that exceptions are under-tested by developers, and therefore it is useful to automatically generate tests for exceptions and boundary conditions. Hence, the goal of this work was to automatically generate executable test inputs with oracles for exceptions and boundary conditions from structured natural language informal specifications. And I present to you Swami, an end-to-end test generation tool that takes as input a specification document which encodes all these challenges and outputs executable tests encoding oracles for exceptions and boundary conditions. I encourage you to go through our paper to know more details about Swami's architecture. In the subsequent slides, I'm going to describe how Swami works with the help of an example. The step 1 of Swami's approach involves identifying specifications which encode testable behavior. As described before, the input to Swami is a specification document that has hundreds of pages and sections, and not all of these may encode testable behavior. Now, when the format of the specification document is known, Swami uses a rule-based approach, where rules are nothing but regular expressions composed of part-of-speech tags, keywords, and wildcard characters. For example, here are some of the rules that Swami uses to match the heading and body of the specification sections to determine whether they are relevant or not. When the format of the specification document is unknown, Swami uses an information retrieval based approach in which it requires access to the implemented source code. For a given specification, Swami computes the similarity score of that specification with the implemented Java classes, and if the computed similarity score of the specification is above an empirically determined threshold, the specification is considered as relevant. Here, the slide shows you an example of a specification which encodes testable behavior. The specification describes a method string.startsWith of JavaScript, and the slide shows you the regular expressions that match the heading and the body of the specification. Once a relevant specification is found, Swami parses and extracts the method signature from the specification heading and initializes an empty test template. For example, in this case, Swami extracts the method name and method arguments from the heading and uses them to create an empty test template. In all the subsequent slides, the code snippet inside a green box with the Swami logo at the bottom right corner shows the automatically generated code using Swami. In this step, Swami also stores the source code that is required to invoke the method under test. In step 3, Swami parses the specification text to identify all the assignment statements and extract and store all the local variables and their values in a separate database. For example, in this case, there are 8 assignment statements, and the table shows to you the extracted local variables and their assigned values stored separately. In step 4, Swami parses the specification text to identify all the conditional statements which contain oracles embedded in them and extracts the information from such statements to populate the conditional templates. Since we are dealing with two kinds of test oracles, namely boundary condition and exception, Swami uses two types of conditional templates corresponding to these. Exception template has an if condition to check if inputs satisfy the exception condition and a try-catch block to verify if the desired exception is thrown by the implementation. The boundary condition template, on the other hand, just has an if condition to check if the inputs satisfy the boundary condition and a test constructor to check if the desired expected output is obtained by the implementation. Swami uses a set of rules to identify if the conditional contains an exception or a boundary condition oracle. For example, in this case, the top conditional statement contains an exception oracle embedded in it, whereas the bottom two conditional statements contain boundary condition oracles. So for the top conditional statement, Swami parses the statement to populate the exception template, the things that are shown in the red, and it creates a source code corresponding to that conditional statement. For example, in this case, the condition of the template is obtained from the specification sentence. The method invocation code is obtained from a previous step, step 2. The test constructor is input by the developer because it depends upon the implementation. For example, Node.js uses assert.strict_equal, and the expected error is again obtained from the specification text. Swami does similar kind of processing for the boundary condition oracles and populates the boundary condition template. Hence, we end up generating this code. Note that the generated code won't compile because it contains local variables and implicit operations described using natural language phrases, the things that are shown in red color here. So in this step, Swami recursively substitutes the local variables and implicit operations using the pre-stored mappings until all the variables are either described in terms of method arguments or JavaScript keywords, which results into this code. Next, in step 6, Swami adds each conditional code to an empty test template that was initialized at the beginning of the process and checks if the code compiles. The code that is shown here will not compile because there is no isRegex method in JavaScript, which is an abstract operation described in the JavaScript specification document. Hence, to handle such abstract operations, which are nothing but simple lookup operations, we manually implemented them using 100 lines of JavaScript code. For example, here isRegex method checks whether the argument is an instance of regex class or not. The implementation of these abstract operations is prepended to the generated test template, and Swami again checks if the generated test template now compiles for each conditional statement. If for some reason the generated template does not compile, Swami terminates the process and moves on to the next step. In our current running example, Swami successfully generated compilable code corresponding to both kinds of conditional statements, and the slide shows you the test template that encodes the oracles which are extracted from the specification, as well as the abstract operations that are prepended to the test template. However, this is just a function which encodes the oracles and will not execute the method under test by itself. Hence, in the final step, Swami instantiates the generated test template using random input generation along with using certain heuristics that can help reduce false alarms. For example, in this case, the method under test string.starts_with accepts three inputs, and the first input, this object, is used to create a string object. To avoid creating false alarms while invoking string constructor, Swami's random input generation module ensures that this object's value is a valid string. Swami asks the user to specify the number of test inputs to be generated and generates those many unique combination of test inputs. Since many of these randomly generated test input combinations will not satisfy the conditions that can trigger the exception and boundary condition, Swami ends up generating a lot of innocuous tests. Hence, starting from a given specification of string.starts_with method, I showed to you how, using Swami, we generate executable tests which contain abstract operations, test template that encodes derived oracles, and test inputs that can be used to exercise the derived oracles. Swami generated such test files for each relevant JavaScript method, which we integrated with the Mozilla Rhino and Node.js test execution infrastructure. To remind you, I already talked about Swami's evaluation at the start of the video. We evaluated Swami on the official JavaScript specification, looking at how precise are its tests and if it does better than humans in the state-of-the-art tools. We found that 98.4% of the non-innocuous tests Swami generates are precise to the specification, and it improves on the developer-written and generated test suites. Finally, looking at the popular implementations, Swami found one new bug in Rhino and Node.js, and 15 missing features in Rhino, some of which are being implemented by Rhino's developers after we deported them. Swami also found 18 ambiguities in the specification that Rhino and Node.js developers interpret differently. To conclude, I described to you Swami, a test generation tool to automatically derive tests with oracles from specifications, and its evaluation on JavaScript specification using Mozilla Rhino and Node.js. The implementation of Swami is available for free to download and reuse at our website swami.cs.umass.edu. Thank you.